Good evening all. Good evening all. Welcome to week 7 of the NPTEL live session for Engineering Thermodynamics course. We'll wait for a couple of minutes and then we'll get started with this week. So this week we'll be discussing on flow processes. So up until now we have been discussing problems where the mass of the system remains constant. But now we'll be discussing control volume concepts where the mass of the substance inside the boundary actually no changes. That those are the unsteady processes, and then we have steady state processes where there is a mass flow across the boundary, but then the total mass within the boundary remains constant. Just share my screen. My screen is visible. We'll wait for a couple of minutes and then we'll get started with the problem. In the meantime, you can go through the problem and attempt it yourself before I start discussing. Just to avoid confusion between in these problems, just to avoid confusion between internal energy and velocity, I've been using a different notation. So here C stands for the velocity, U is for the specific internal energy. I guess we should get started. So first problem here, 10 kg of fluid per minute goes through a reversible steady flow process. The properties of the fluid at the inlet and outlet are essentially given here. So P is earth pressure, rho is the density, C is velocity, and U is the specific internal energy. During the passage, the fluid rejects 55 kJ per second and raises to 55 meter. Determine the change in enthalpy and work done during the process. So how do I find the change in enthalpy again? As we have been discussing this so many times, so enthalpy is again a property. It's basically a point function, so it only depends on the initial and final states. So the change in enthalpy is given by H2 minus H1, exit minus inlet, where but the enthalpy is not given here directly. So how do you evaluate that? So what is H? Is U plus PV. So I can write this as U2 plus P2 V2 V1 V1. So that is delta U P2 V2 minus P1 V1. Pressures are already known. U2 minus U1 are already given. So you can directly substitute them back. So what else is missing? How do I get the specific volume? So density is provided here. So specific volume is 1 by rho. So specific volume is basically 1 by rho. So since rho is provided, I can directly use it to substitute back here. So how do I get delta H now? U2 minus U1 10 minus 910 plus P2. V2 is basically V2 100 just to convert it into kilojoule per kg minus P1. If you want to calculate the total change in enthalpy per unit weight, so you already know the mass flow rate, m dot is given. So m dot is 10 kg per minute. So total change in enthalpy or THDT. I'm denoting with H dot. H dot is THDT. Is m dot times delta H. How do you calculate the work done? Again, we use the steady flow steady state energy equation. What is the equation? We have Q dot minus Wx dot is basically the shaft. I'm just using X to represent the shaft work from this one, but or else you can neglect that. You can just write Q dot minus W dot is del ECV dt plus m dot H out minus H in plus m dot, or just to be consistent with the notation here, out is exit, so write H2 minus H1 plus m dot C2 square minus V1 square by 2 plus m dot G delta G, where delta G your change in elevation. So in this case, so it is given it is 55 meter and it rises, so this will be positive. If you, since it is a steady state process, so it is already given that this is a reversible and a steady flow process, so we make this equal to 0. And it says that the fluid rejects 55 kilojoule per second. So Q dot is negative. So this is minus 55 minus W dot. M dot times delta H, we have already calculated it. C2 square minus C1 square. And this will be in joule per second. So I just wanted it into kilojoule. So I'm dividing it with 1000 plus. So let's just take the value of G to be 10 and delta Z is 55. By again, this is will be in joule per second. So I'm converting it to kilojoule per second. Okay, is this clear? Are there any queries? I guess there are no queries. And all of the problems that we are going to discuss today are going to be falling into one of these two. Basically, you will be using the same equation. So Q dot minus W dot is that is what is this in case of the change, like in case of an unsteady process, this no not this will be some finite value, and in case of steady flow processes, this will be 0 plus m dot H out minus H in, and out v velocity V out square minus V in square by 2, and then is V out minus V. The change in potential is kinetic plus the enthalpy changes will give you the net change of This will be the net internal energy change, which will again be equal to Q minus W, Q dot minus W dot. So either you will be asked to find Q dot, or you will be asked to find W dot, or you will be asked to find H2 minus H1, for which you need to be given this, like, for example, if it's an insulated state, this will be zero. In different cases, we'll see different problems where out of all these terms, a few terms will be known, and one of the term will be unknown, and this is just one equation, so we'll be solving for that particular term. Okay. That being said, we'll move on to the next problem. Hey, in a gas turbine unit, the gases flow through the turbine at 15 kg per second, and the power developed by the turbine is 12 megawatts. The enthalpies of gases at inlet and outlet are 60 kJ per kg and 400 kJ per kg respectively, and the velocity of gases at inlet and outlet are 50 meter per second and 110 meter per second respectively. Calculate the rate at which heat is rejected from the turbine and the area of the inlet pipe, given that the specific volume of the gases at inlet is 0.45 meter per kilogram. So how do you go ahead with this for all? So first thing you need to observe here is mass flow rate is given, which means it is not a system anymore. So you have to use a control volume approach. So in a control volume approach, you have, and it also says that this velocities etc. are given. So you'll go with the equation. First you write the equation. Since nothing is specified about this, or usually whatever the case is, in case of turbines and all these things, you can actually neglect the changes in potential energy when you are dealing with gases. Whenever there is a gas, the densities will be pretty low. You can actually neglect the changes in potential energy. But for now, I'm just writing that down. So now you look for the terms that can go off. First thing is you start by assuming that all of these processes are steady state processes because the mass m dot in is m dot out. So this term goes to 0. Next, m dot is already given. So what are the information that is given? M dot is given as 15 kilogram per second. And do I know H2 and H1? Inlet and outlet it is given. Inlet is H1. Outlet is H2. So in case of a turbine, we are getting work out of the system. If turbine is my system, so if you consider this as your turbine, if I draw a boundary like this, we are extracting net work from the turbine. So work done is positive, and it is given as 12 megawatt. So I'm just 12,000 kilowatt. Do I know C1 and C2? The velocity of gases is inlet and outlet are 50 meter per second and 110 meter per second. So in this equation, we are assuming that Z2 minus Z1 is very much less than change in kinetic energy plus delta H. So we are neglecting this term. So what do I have now? I need to find Q dot. So Q dot minus W dot is already known. Is M dot times H out minus H in plus C2 square minus C1 square. Just to be consistent with the units, I'm dividing with 1000. just to differentiate between heat and work. For heat, I'm just writing kilojoule per second, and for work, I'm using kilowatt. Okay. What the next part of the question asks to find the areas of the inlet pipe, given that the specific volume of the gases at inlet is so and so. So how do I calculate the area of the pipes? We know m dot, so m dot can be written as rho a1 c1, c is your velocity, rho 1 a1 c1. Since it in inlet specific volume is given, so this can be written as a1 c1 by v1, and we are required to find a1. We know all of these values. We know m dot as 15 kilogram per second. We know the initial specific volume as 0.45, and we also know the initial velocity as 50 meter per second. Are there any queries? If there are no queries, I guess we'll move on to the next problem. So here you have an air compressor, and air flows steadily at a rate of 0.5 kilogram per second, and then it's a steady process, so it goes in and then it goes out at the same rate. It enters the compressor at 6 meter per second with a pressure of 1 bar and a specific volume of 0.85 meter cube per kilogram, and leaves at 5 meter per second with a pressure of 7 bar and a specific volume of 0.1 meter cube per kilogram. The internal energy of the air leaving is 90 kilojoule per kg, greater than that of entering. So exit internal energy is greater than the internal energy, entering internal energy. Cooling water in a jacket surrounding the cylinder absorbs heat from the air at a rate of 60 kilojoule per second. So if I consider this as my system, so there is a heat energy that is being extracted out of this control volume, and that is equal to 60 kilojoule per second. Or calculate the power required to drive the compressor, which is which will be, say for example, if you are driving this compressor using a motor, you need to know this power so that you can rate your motor accordingly. Second, inlet and outlet pipe cross-sectional areas. So what is given? We know m dot, and we know it enters the compressor. So the compressor inlet is known. We know the initial pressure. We know the initial specific volume. We know the final velocity, final pressure, and we also know the final specific volume. And it is given that the internal energy of the air leaving is 90 kilojoule per kilogram, greater than that of entering. So U2 is 90 plus U1. So U2 minus U1 is 90. So if I know U2 minus U1 and I know the pressure, so I can calculate the enthalpy change. So H2 minus H1, this was our first problem in today's video. So we have U2 minus U1. This 10 square is just to account for the conversion from joules to kilojoules. So basically pressure is in bars, so I'm multiplying with 100 so that you will convert it to Pascal. The total value will be in kilojoule per kg. Now we have our delta H. Now we apply the steady state energy equation. We have Q dot minus W dot. Since there is one inlet, we can directly take M dot out. And I'm neglecting the changes in potential energy. So we know Q dot here. Q dot is already specified. That is heat being removed from the compressor. That is minus 60 kilojoule per second. So this implies Q dot is minus 60. Work is something that we need to find out. Again, this 1000 is just account for the units. So from this you get W dot equals to, since it is going to be anyway negative, I'm just taking the minus sign towards the other side. So the power required to drive the compressor is around 1.5 kilowatt. Now you need to find the inlet and outlet pipe cross section. So how do you go about doing that? We know M dot, so again just as before, you know M dot, you know what is the specific point of inlet and outlet. So M dot is basically A1 C1 by V1, and that will be equal to A2 C2 by V2. Are there any queries? Okay, if there are no queries, then we'll move on to the next problem. A centrifugal pump delivers 50 kg per second water. The inlet and outlet pressures are 1 bar and 4.2 bar respectively. The suction is 2.2 meter below the center of the pump, and delivery is 8.5 meter above the center of the pump. The suction and delivery pipe diameter are 20 centimeter and 10 centimeter respectively. Determine the capacity of the electric motor to run the pump. So how do you determine the capacity of electric motor? That comes from the work done that you are going to do. So again, you start with the steady energy equation, and from there you need to find the work done. So what is the given information? We know the mass flow rate. Inlet and outlet pressures are already given. If you consider the reference as center of the pump, C1 is minus 2.2 and C2 is 8.5. and it is known that it is water. So we can take density to be okay. So again, if we start by applying the study flow equation, we're assuming that the change in temperature for the water as it rises from below to the above is actually negligible. So we are assuming this to be close to zero. M dot is already given. So how do I calculate C1 and C2? So we know M dot is given by A1 C1 by V1. V is your specific volume, and since it is a circular diameter, like the delivery pipe is a circular, so A1 is 5D1 square by 4V1. So from this you calculate C1. Similarly C2. Since water is incompressible, the initial and final and initial densities are going to be same, so specific volumes are also going to be same. And we are assuming it is insulated. So we have now again here we are assuming that the motor is 100% efficient. So if the motor is 100% efficient, then this will be the work that the motor has to do in order to raise the water from here to here. But however, if the motor is not 100% efficient, so if say eta is the efficiency of the motor, then power required is whatever W dot that you have calculated here divided by eta. So this should be the power of the motor that you should be using to do this particular task. So in this particular problem, we are assuming beta is 1, or basically 100%. Are there any queries? Yeah. There are no queries, then we move on to the next problem. During flight, the airspeed of a turbojet engine is 50 meters per second. Ambient air temperature is minus 14 Celsius. Gas temperature at the outlet of nozzle is 610 Celsius. Corresponding enthalpy values for air and gas are respectively 250 and 900 kJ per kg. Fuel to air ratio is 0.018 and the chemical energy of fuel is 45 megajoule per kilogram. Owing to incomplete combustion, 6% of chemical energy is not released in the reaction. Heat loss from the engine is 21 kJ per kilogram of the air. Calculate the velocity of exhaust. So this is your engine inlet and exhaust. If I'm considering a control volume and outlet, there is a net heat output. So what is given here? So we know the air speed of the turbo engine, which will be equal to your C1, and you also know the ambient temperature. So the engine is taking air from the ambient, so that will be your inlet temperature. You also know the exhaust temperature. Enthalpy values at inlet and outlet are given. So H1 is again, just to be consistent, here we have two different things. We have a fuel. It's like while entering, it was just the air, but inside the turbine, you have certain fuel. So the air will mix with the fuel, and then both of them will come out here. So just to be consistent, I'm using H1 is of air, so I'm just using a superscript A to denote that it is for air. And H2 air is 900 kilojoule per kilogram. It is given that the fuel to air ratio is 0.018. So suppose if uh, air is 1 kg per second, then fuel is going to be 0.018 kilogram per second. Since the fuel to air ratio is this, the chemical energy of the fuel is 45 megajoule per kg, and due to incomplete combustion, 6% of it is net released in the reaction. So is not released in the reaction, which means the change in internal energy of the fuel, basically the energy that is converted into the that is actually used by the turbine engine, is only 94% of it. That is 94 times this total energy, 45. And we need to determine the velocity of the exhaust. So we need to find C2. Second, we start from the, it is also given Q dot is heat loss from the engine per kg of air. So if I write my equation, so m dot air times the Q dot that is given minus, or let us do it in this way. So there is a net. So since it is 1 kilogram per second, I'm just using 1 here. Or let us put in a slightly different way. So just to be consistent. So here you have a change in internal energy of the fuel, and all of this internal energy is getting converted into other stuff. So what is your inlet and what is at your outlet? We'll do that. So at the inlet, I have my initial velocity to be 250 meter per second, and that is only air. So air mass flow rate is 1 into C1 square into 1000 plus the at inlet, we know it is m dot is 1 into 250 kilojoule per kilogram. That is the H inlet. At outlet, we have a velocity of C2 square. That is something that we need to find out. And we know the outlet enthalpy. That is mass is 1 times 900. And then we have a net heat reduction minus 21 kilojoule per kilogram of air. Air mass flow rate is 1. And then we have the fuel. This delta U is for the fuel. So at the fuel, how much of it is converted? It's only 94% of it. So this times multiplied by the mass flow rate of the fuel, which is 0.018 kg per second. So just to convert into units. So this is for the velocity part, this is the enthalpy part, this is Q part, and this is the U part. So whatever is the heat loss plus whatever is your change in internal energy, this is the change in internal energy, out of which 21 kilojoule per kg is lost, and these are the inlet and outlet changes. So from this you get C2 square there any queries? Or if you want to come from this normal way that we have been doing, so like in case of fuel, like we are considering this change in chemical energy is basically the energy that is being generated from the fuel. So that comes here as an additional term, unlike our previous equation. And then you have m dot a times, I think there is some mistake we have done, m dot a times C1, sorry, outlet minus inlet. So air is also leaving, plus your fuel is also leaving as an exhaust, while only air is entering. The change in the potential energy is neglected. So if I divide the entire equation with m dot a, I think there was a mistake here. So Let's divide the entire equation with m dot a. This is the chemical energy one. So this is per, as you see here, the Q dot is given as per kilogram of air. So this turns out to be that minus 21 H2 minus H1 plus fuel to air ratio is given. Delta U is, so initial energy is this, and after the reaction 6% is not released, so 94% is released, so that is your 42.3. And in this we need to also, for okay, there is one more thing that you have to ask me, that about what is happening to the work done here. So we need to know the process that is happening here. So we have to assume certain process for it, and then we have to calculate the work done part. So there is a work done here that needs to be calculated as well. So how do I calculate the work done? We already know from the previous case that this will be very okay. So again, work done, we need to determine what is the process that is happening. You can assume a certain process, and then from there you can calculate the net work done. You can assume that the air here is undergoing like this heat, whatever is released is basically, you can assume that is not from the air. So you can assume an adiabatic process for the air. It's a very fast process, so air is not undergoing any of these changes. So in that case, what will be the work done? The specific work done for the air, that is basically the net work that you are extracting from this. We will keep that as y for x y. So let's assume that you are not extracting any work from this. So I think I missed certain portion in the problem. We need to calculate the work from here. How do I calculate the work in this case? I think some part of the problem is missing. I'll get back to this in the next week. So we'll move on to the next problem for a while. Sorry for the confusion. So we will discuss this in the next week. Okay, we'll move on to the next problem. So air at a temperature of 20 Celsius passes through a heat exchanger at a velocity of 40 meters per second, where its temperature is raised to 820 Celsius. It then enters a turbine at the same velocity of 40 meters per second and expands till the temperature falls to 620 Celsius. On leaving the turbine, the air is taken at a velocity of 55 meters per second to a nozzle, where it expands until the temperature has fallen to 510 Celsius. If the air flow rate is 2.5 kg per second, calculate the rate of heat transfer to the air in the heat exchanger. power output from the turbine assuming no heat loss, and velocity at exit from the nozzle assuming no heat loss. So here we have an heat exchanger, and then from there it goes to the turbine, and from turbine it goes to the nozzle, different stages. So all we need to do is calculate each of this. Calculate the heat transfer in case of a heat exchanger, calculate the power output in case of turbine, and calculate the final velocity in case of a nozzle. So how do we start with all of them? Start from the same equation, but then we will see how different terms will be changing in this. So initial temperature is given as 20 Celsius, and the final as it passes through the heat exchanger. So first for the heat exchanger, inlet temperature is given, outlet temperature is given, and you know that the velocity remains constant. So C1 equals to C2 is 40 meter per second. We're assuming there is no change in velocity. So how do I calculate this is air. So how do I calculate the net heat transfer in heat exchanger? It is m dot Cp delta T. So m dot Cp T2 minus T1. This is your net heat exchange. So m dot is already given. For air, you can assume Cp to be 1 kJ per kilogram times your delta T. That is straightforward. Now for the case of a turbine, assuming there is no heat loss, again you start with the same equation. So Q dot is 0. So the net work output from the turbine is, if you recollect from your lecture videos, we have Q dot minus Wx dot, or just W dot, H2 minus H1 plus T2 square minus C1 square by 2, neglecting the changes in potential energy, and then Q dot is also 0. So the net work done, in case of a turbine, it will be m dot times H1 minus H2, C1 square minus C2 square by 2. And it says that it then enters a turbine with the same velocity of 40 meter per second and expands till the temperature falls to 620 Celsius. So the final temperature is 620 Celsius, initial temperature is 820 Celsius. So H in case of air is Cpt, so m dot is 2.5 times Cp is 1 kilojoule per kilogram times delta T. So T1 is 820, it falls to 620. On leaving, the air is taken at a velocity of 55 meter per second. So the exit velocity is 55 meter per second, and the inlet velocity is 40 meter per second. This 1000 is just for conversion of units. Now again, if you apply the same equation in case of a nozzle, again there is no heat loss and there is no work done in case of a nozzle. So you have H1 plus C1 square by 2 is H2 plus C2 square by 2. It says that the final temperature is 5 degrees Celsius. So H1 minus H2 you need to determine C2. So C2 square by 2 is H1 minus H2, which is Cp times T1 minus T2. T1 is the exit temperature of the turbine. The exit temperature of the turbine is 620 Celsius minus the inlet temperature of the nozzle. Sorry, the exit temperature of the nozzle plus the inlet nozzle velocity is given as 55 meter per second. This is just to convert into appropriate units. Are there any questions? Okay, we'll move on to the next problem. An air receiver of volume 5.5 cubic meter contains air at 16 bar pressure and 42 degrees Celsius temperature. A valve is open and some air is allowed to flow to the atmosphere. The pressure of air in the receiver drops rapidly to 12 bar. The valve is then closed. Calculate the mass of air that left the receiver. This is an unsteady process. So volume of the container is given, which is 5.5 meter cube, which is again a constant. So initial pressure is 16 bar. Initial temperature is also given, and then final pressure is given. To calculate the mass of air that left the receiver, all we have to do is calculate what is the initial mass, calculate the final mass, and the difference will give you the mass that has left. How do I calculate the initial mass? We use ideal gas equation, air follows ideal gas law. So we have N1 as P1V by RT1. P1 is 16 bar, V1 is 5.5 cubic meter, by R is 287 kJ per kilogram Kelvin, and then temperature is 42 Celsius, which is 315 Kelvin. Now I need to find the final mass. So final mass will be P2V by RT2. I know P2, I know the volume, I know the R value, but I don't know the value of T. How do I calculate the final temperature? So here again, the one that we have been discussing in the first week, where it says that there is a rapid process. Whenever there is a rapid process, you can assume that the process is so fast that whatever is inside the system doesn't get enough time to exchange heat with the surroundings. So you can assume it to be an adiabatic process. So in case of an adiabatic process, that could be one way. So, or so how do I do that? How do I determine the final temperature? So can I use this relation? The answer would be no, because as we have been discussing up until now, this relation is based on the assumption that your mass remains constant. But here, if you have here you have something where you have the mass is continuously changing. So if you consider this as your vessel that is connected to some valve, and this is my boundary. When the valve is open, the mass inside the container is continuously decreasing. The volume is constant, but then mass is continuously decreasing. So you cannot directly use the relation T1V to the power or PV to the power gamma equal to constant. So what can I do about it? So again, you start with your equation Q dot minus W dot is dt plus H out minus H in. I'm just writing out and in. Uh, like we are neglecting the changes in kinetic energy and potential energy. But we know one thing here that and we have the mass equation where dmcv dt is mass increases. So if converting mass and that out, so m dot n is 0. Since there is nothing that is coming inside, so I've just removed the other term here. So there is no inside term, there is only external one. and there won't be any work done because there is no work interaction that is happening here, and this is basically volume of a container of a constant volume. So how do I calculate m dot out? So basically dmcvdt is minus m dot out, and this comes as dcvdt is ddt of mcv times ucv. mcv is pressure times volume of the container is constant by RT times UCV is CV times T. So as I said before, if you can assume that when there is a very rapid process, you can assume it even adiabatic process, there is no heat exchanges, so your Q dot will also be zero. Now this leaves us with dCV dt is CV, you can write it as R by gamma minus 1. So I'll just leave it as CV by R times volume times dP dt. But let me put it in the same way. So you have ddt of mcv times ucv plus h out is cp times t out times m dot is minus dmcv dt. So if you just do a little manipulation here, so ucv can be written as cvt cp by cd is gamma, so ddt of mcv t is gamma t times dmcv dt. If you do the integration, final mass by initial mass is 1 by gamma minus 1, final temperature by initial temperature. And like as we said before, you can use ideal gas law. So N2 by M1 is P2 by T2 times P1 by T1. We know P2 and P1. So it is from 16 bar to 12 bar. So 12 by 16 times initial temperature is also known as 42 Celsius. You substitute that back. So we have ln 36.25 minus ln T2. For air, you can take gamma to be 1.4. So 1 by 0.4 times ln T2 minus ln T1 is 315. This gives me so once I calculated the value of T2, mass is straightforward. So you can calculate M2 to be 236.25 into M1. M1 we have already calculated before as 97.339. Now we know the initial and final masses. So the mass that has left the container is M1 minus M2. So the difference between this problem and the previous problems that we have discussed up until now is that this is an unsteady process unlike the previous ones. So what is the only thing that we have done? So we know that the final mass, to calculate the final mass, we need to know the final temperature, but then we cannot directly use the relation PV to the power gamma minus 1 equal to constant because mass of the system is continuously changing. So we use the energy equation here. So Q dot minus W dot is del E C V del T plus m dot out H out, and there is no inlet, so I'm neglecting that, and changes in kinetic and potential energy are also neglected. And we know the equation for mass is dmCv dt is m dot in minus m dot out. So this is quite easy. So if m dot in is higher, your Cv mass will increase. Otherwise, it will decrease. But in this case, there is no inlet, so this is again 0. So then we use the relation that dmCv dt plus. So since Q dot and W, why is Q dot 0? It's again because it is a very rapid process. In case of rapid process, it doesn't have enough time to explain, so you usually neglect the Q dot. So Q dot minus both are 0 since there is no network interaction as well. So from this we get dCv dt is, maybe I'll just keep it here. So dECV dt is ddt of ECV is basically m times u. So I substituted that here plus m dot out h out. So m dot out is minus dmCv dt times h out is Cp times t. So if we just do some mathematical manipulation here, so we got this final equation as like dt dt gets cancelled, and then you eventually get dmCv by mCv is dt by t times gamma minus 1, and then you do the integration, and then you substitute all the values to get the final mass, final temperature. From the final temperature, we use ideal gas law to calculate the final mass. Once we know the initial and final masses, the change will give you the delta m is what is asked in the problem. Are there any queries? Yeah, I guess there are no queries. So we'll move on to the next problem. So up until now we have been discussing again on air. Now comes steam. So you might have to refer to the steam tables again. So steam at a 7 bar and 200 Celsius enters an insulated convergent divergent nozzle. So what I mean by convergent divergent nozzle? You have something like this. It doesn't look good. So this is your converging part and this is your diverging part. This is your boundary. So it is given that the entering pressure is 7 bar and T1 is 200 Celsius, velocity 60 meter per second. It leaves an nozzle at a pressure of 1.4 bar, and final enthalpy is also given. You need to determine the final velocity. For a nozzle, like you assume that it is an insulated one, it is given here is insulated, so your Q will be 0. So nozzle, you don't extract any work from the nozzle, so W is also 0. So you have H1 plus C1 square by 2, H2 plus C2 square by 2. You are asked to find C2. The only thing that I don't know in this equation is the value of H1. How do I calculate H1? Again, you refer like the pressure and temperature are given, so you can directly look up from the steam tables and then calculate the value of H1. So 7 bar in 200 degrees Celsius, so that is in the superheated region. I'm not going through much of the details again, so we'll directly go over to the steam tables, and then you can directly check that if the pressure is 7 bar, at 7 bar, so at 7 bar your saturated temperature is 165, but then temperature that is given in the problem is 200 Celsius. So you have to refer to the superheated steam tables. So if you go to the superheated tables for a pressure of 7 bar, we have the value as the temperature is 200 Celsius. So the value of H is 2844.8. So we'll directly use that value. Joule per kilogram. So from this, if you directly substitute, sorry, 2 goes inside the square root. This is very straightforward, so I don't think you have any queries. So we'll move on to the next problem. A compressor takes air at 100 kilopascals and delivers the same at 550 kilopascal. The compressor discharges 16 meter cube per minute of air. The densities of air at inlet and exit are 1.25 kg per meter cube and 5 kg per meter cube. The power of the motor driving the compressor is 40 kilowatt. The heat lost to the cooling water circulated around the compressor is 30 kJ per kg of air passing through the compressor. Neglecting changes in kinetic and potential energy determines change in the specific internal energy. So again, what are all given here? So we know that initial inlet pressure is 100 kilopascal and final pressure is 550 kilopascal. And the compressor discharges at so and so. So the discharge is V dot 2, that is volume flow rate, 16 meter cube per minute. Densities at inlet and exit are given. So rho 1 is 1.25. Rho 1 and rho 2 are given. The power of the motor that is driving the compressor, just to differentiate. So W dot motor is given as 40 kilowatt. Is the work done on the motor? So I'm just putting a minus here. Or okay, the heat lost to cooling water Q dot, it is lost. So I'm just putting minus 30 kilojoule per kg of air. Now what is asked is you need to determine the change in specific internal energy. So how will I proceed with this? So can you start with the equation Q dot minus. So from our first problem itself, this is delta U plus P2. P2 is specific volume, so I'm directly writing by rho 2 by P1 by rho 1. But m dot is not directly given here. So how do I calculate m dot? Volume flow rate is given, and then it is said that it is at the discharge, and you know the density of the discharge. So m dot is basically rho 2 times V2 dot. So I just divide this entire equation with m dot. We have Q dot by m dot is Q minus W dot by m dot is delta U. That is, this is what we are trying to find, changing specific internal energy, plus the final pressure 2 minus P1 by rho 1. And m dot I'll just write it as rho 2 V2 dot. So Q is given as minus 30. Work done is basically 40 kilowatt is negative, minus 40 by rho 2 V2. Rho 2 is given as 5 kilogram per meter cube, and then V dot 2 is 16 meter cube per minute. To convert it to second, you just multiply with 60. It's delta U plus the final pressure. I'm just leaving it in kilopascal so that the entire thing will be in joule per second. By rho 2 is 5 minus initial pressure by initial density. Are there any questions? I guess there are no questions, so we'll move to the last problem. So in a water-cooled compressor, 0.5 kilogram of air is compressed per second. A shaft input of 60 kilowatt is required to run the compressor. Heat lost to the cooling water is 30% of the input, and 10% of input is lost in bearings and other frictional effects. Air enters the compressor at 1 bar 20 Celsius. Neglecting the changes in kinetic and potential energy, determine the exit temperature. Consider a steady state and Cp equal to 1 kilojoule per kilogram Kelvin. So we know m dot is given as 0.5 kilogram per second, and the shaft input of 60 kilowatt is required to run the compressor. So you know W dot shaft is given as 60 kilowatt, and it says that the heat loss to the cooling water is 30% of your input. So Q dot is minus 30% of your input is 60 kilowatt. This is minus 18 kilowatt. And 10% of the input is lost in bearings and other frictional effects, which means out of the total input energy that you are giving, 10% is lost to bearings, so which means that is not actually converted into work. So W dot is Air enters the compressor at a pressure of 1 bar and a temperature of 20 Celsius. Neglecting changes in kinetic and potential energy, determine the exit temperature. So you again use the steady flow steady state energy equation. So Q dot minus W dot is m dot. H dot minus Hn, we use Cp times T2 minus T2, T2 minus T1. We know Q dot to be minus 18 and W dot to be minus 54. M dot is already given. Cp assuming 1 times T2 minus T1. To solve this equation, T2 comes out to be this is also a very straightforward problem. So I don't like to spend much time on that. Are there any questions? Yeah, I guess that's the questions that I have for this week. So there is one question, one problem that we have left in the beginning. Maybe if you can discuss, we can discuss this again. So I'm drawing two outlets here. This is for the fuel. This is for the air as exhaust. This is the inlet. So maybe if we change this question a little, change in enthalpies are given like this. So change in enthalpy for air, that is H2 minus H1, for air is given to be 250 per kilogram, and then for fuel, or basically the gas, H2 is for the gas. Gas is a mixture of air plus whatever is basically after combustion, whatever is your output, it contains air as well as some of the uncombustion products or whatever is left inside the gas. So that is your gas. So maybe I think I missed out a part of the question here. We'll assume that this enthalpy is with respect to unit mass of the air that is leaving, and then we have the fuel ratio m dot f by m dot a to be 0.018, and chemical energy of the fuel is so and so. So initially, chemical energy of the UF1 is 45 per kg, and UF2 is 6% is left, so you have 94% remaining. So basically 6 is not released, so finally is 0.06 times 45 megajoule per kilogram. And this kilogram is of the fuel. And heat loss is given. If we start with our equation, so we have Q dot minus W dot. This M dot, one inlet is first we'll start with outlet. So M dot air times the outlet H2 plus, sorry, minus M dot A times H1 plus M dot A C1 square by 2 plus there is some fuel also that is getting exhausted, C2 square by 2 minus m dot a C1 square by 2, and then we have dCvdt. So this, so what is changing inside the system is your chemical energy is changing. So this is ddt of your fuel times whatever is the change in of fuel, this one. So this will be m dot f times uf2 minus uf1. This is to convert from megajoule to kilojoule. So up until this, everything is clear. So the problem that we were stuck previously is all we need to find is calculate the value of C2. But then to do that, we need to know the value of work done as well. So if I divide the entire equation with m dot a, so I'll just denote it as Q minus W dot by m dot a, H2 minus H1 plus the fuel ratio times C2 square by 2 minus C1 square by 2 plus change in internal energy. Internal energy of the CV is actually decreasing, minus m dot f by m dot a. You are required to find C2. So I substitute those values. So we have minus 21. This is just for the unit conversion. Minus C1 square by 2. So in order to determine this work done, we need to be doing the process that has undergone. So if we assume the work done to be 0, so basically if we assume that this turbine jet is not rotating any of the shafts, which is usually not the case. So the turbine shaft has to be like whatever is energy that is being generated from this has to be will be rotating your engines. If we neglect that part, then if W equal to 0, then the exhaust velocity will be 488.87 meters per second. But if that's not the case, that is basically you're generating some power from this turbine turbojet engine, then you will have certain value of W. So W will not be equal to 0, and depending on whatever your value is, you can your value. So for example, if W is positive, so this increases, so your exhaust velocity will change accordingly. So if this increases, exhaust. So if you see the values here, so for example, if W is some positive value because you are extracting work from the engine, so this increases, so the difference decreases and C2 will decrease. So as you extract more and more work, your exhaust velocity decreases, so your thrust decreases. But if you do not want to extract the work from it, then your thrust will be maximum, but then you are not extracting any work from it. So I think this is some trade-off that you have to work out. Okay, so are there any questions in this? So I guess there are no questions, and these are the like we discussed around 10 problems. So these are the problems for this week, and we'll meet the same time next week. Thank you for joining and the session for today. Thank you.